Today we're going to be starting to look at colligative properties of solutions. And we're going to focus on one particular colligative property of a solution, one known simply as vapor pressure lowering, which is also known as Raoult's law. So what is a colligative property? Well, a colligative property is pretty simple. It's a property of a solution that depends solely on the concentration of solute particles and not actually on the identity of the solute. So the more concentrated something is, the more this particular property is manifested. And the strength to which these properties are exerted depends completely on the intermolecular forces that exist between the solute and the solvent. The stronger those intermolecular forces are, the more of an influence these colligative properties are going to have on the physical property that we're looking at. And so we will be looking today at vapor pressure lowering. That's going to be our focus for today, is this one. In a future video, we will look at these other three, probably in two different groups. We'll look at the elevation of boiling point and the lowering of freezing point, because those two properties are very closely related to each other. And then in one final video, we'll look at osmotic pressure and some other kinds of colligative properties as well. So let's take a look at vapor pressure. Now, we talked about vapor pressure in chapter 6. Vapor pressure is the pressure that is exerted by a gas or a vapor as it evaporates. And so if we have a closed container, where, let's say we have an open container of water here, and we put some kind of covering on it so that the vapor molecules are trapped. They can't get out anywhere. What will happen is that eventually we'll hit a point where evaporation and condensation start to occur at an equal rate. We call that equilibrium. Now, as soon as we take this paper off, these vapor molecules are free to move out, and more water will evaporate to replace the ones that have been lost here. But so long as we keep the system closed, this equilibrium will exist, and we'll have a noticeable pressure that will exert itself on the walls of this container, and that's what we call vapor pressure. Now, we can relate this to, again, we talked about boiling point in the same way, and boiling point is just that temperature where the vapor pressure of the liquid matches the atmospheric pressure above the liquid. And the normal boiling point is when that atmospheric pressure is standard pressure, 1 atmosphere, 760 millimeters of mercury. Now, what impacts vapor pressure? Well, we talked about this stuff here in chapter 6. The idea that intermolecular forces and temperature all are interrelated in terms of vapor pressure. And if you have strong forces, then you need higher temperatures, more kinetic energy to get that liquid to vaporize. The part that we haven't talked about yet, and that leads into our discussion of solvents and solutes here, solutions, is if we have non-volatile solutes, that is, solutes that are not capable of vaporizing anyway, what we see is that the intermolecular forces between solute and solvent are always greater than the solvent by itself. And as a result of that increased strength, we see a depression, a decreasing of the rate of evaporation, a decreasing of the vapor pressure compared to the pure solvent. And we can relate this in terms of something called Raoult's law. Raoult's law says that the vapor pressure of a solution is equal to the mole fraction of the solvent multiplied by the normal vapor pressure of the solvent. And so this value here, the vapor pressure of the solvent, this is a reference value. You'll always be able to get this off of a table of values, or it'll be given to you in some kind of way. It is temperature dependent, however. So when you look up values for the vapor pressure of a solvent, keep in mind temperature is going to impact that vapor pressure value. This value, mole fraction, this is something that we can calculate. And we calculated this in a previous video where we looked at mole fraction overall. And so the product of these two will give us the overall solution vapor pressure. And so the more solute we have in here, the lower our mole fraction will be, and the lower our solution vapor pressure will be as well. And what's cool about this, what makes it a colligative property, is that the identity of the solute does not matter. Doesn't matter. What matters is how many moles of that solute we have and how many moles of solvent there are. Now, the question you may be asking yourself is, well, what if I have a mixture of two liquids and both of them are volatile? They both have vapor pressures. Well, we can use Raoult's law for that as well. The only difference is that we have to integrate the fact that each one of those solutions, each one of those solvents rather, is volatile on its own. And so what we have to do is we basically do Raoult's law for each volatile component, and then we add it together for all of the volatile components to get the total pressure. And so this obviously complicates things a little bit, but it uses the same kind of calculation, it uses the same kind of action. So from that standpoint, yes, it's more difficult, but in a lot of ways, it's the same as the kind of calculations you were seeing in the previous slide. With all of that in mind, let's take a look at a couple of examples. So I'm actually going to skip to example 4 here. And you'll see why in just a minute. Example 3 is kind of complicated. I'm actually going to address it in a separate video. So example 4, a solution contains 100 grams of water and 25 grams of sodium chloride. Calculate the vapor pressure of the sodium chloride, understanding that sodium chloride is not a volatile compound. So we want to know the vapor pressure of this solution. Now, before we can do that, we need to go to a reference. We need to find the vapor pressure of water at 25 degrees Celsius, because we're going to assume, we're not told what temperature this is, but let's just assume it's 25 degrees Celsius. That'll be easy enough to do. So this is an example of one place where you can find this kind of information. This is a website called Wired Chemist. It's got a lot of thermodynamic and other kinds of data here, very similar to what you'd find in the CRC handbook. But what we're interested in for this is we're looking at the vapor pressure of water at 25 degrees Celsius. And so for that has a vapor pressure of 23.8 torr, torr being the same thing as millimeters of mercury. So if I go back to our value here, the pressure of water at 25 Celsius is 23.8 torr. And so that is going to be our known value. Now, to find the pressure of the solution, I need to know the mole fraction of water and multiply it by the pressure of water, which we just established as 23.8 torr. So what we need now is the mole fraction of water. To find the mole fraction of water, I need the number of moles of water and the number of total moles. So pretty easy conversions here. 100 grams of water, which we know its molar mass, it's been given to us, at 18.02 grams of water for every mole of water. And so we put that in right there. Calculator comes up 100 divided by 18.02 will give 5.549 moles of water. Conversely, 25 grams of sodium chloride, same process, 58.44 grams of sodium chloride in every mole of sodium chloride. So once again, grab our calculator, 25 divided by 58.44 will give 0.4278. If I add those two together, I would get plus 5.549 to 3 decimal places, because we have 3 decimal places here and 4 there. We get 5.977 moles total, which means that our mole fraction of water is equal to the number of moles of water, 5.549 moles of water, divided by 5.977 moles total. Which equals the 4 significant figures, 5.549 divided by 5.977, 0.9284. And so putting it into the final equation, the pressure of the solution is going to equal 0.9284 multiplied by 23.8 torr .9284 multiplied by 23.8 to 3 significant figures is 22.1. So we don't see a significant lowering. I mean, it is 1.7 torr, but given that this is such a small concentration of sodium chloride, at least from a molar standpoint, it doesn't have that big of an impact overall. It's only lowering it by less than 10%. So that's how you attack these kinds of problems. In the next video, I'll show you how to attack a problem when you have 2 different volatile solutes, or 2 volatile solvents, depending upon your viewpoint. Until then, take care.